Before we begin, let me introduce myself a little bit. I'm Takeshi from Tokyo, Japan, and I'm currently working for the American company called Tetrate. And Tetrate is service mesh related company. So we are working on Envoy proxy and the Istio control plane and that related open source projects. And I'm actually the maintainer of these two projects, Envoy proxy and Istio, and especially I'm author of, or I'm owning the code base of WebAssembly related plugins or subsystems on these projects. But today's talk is nothing to do with service mesh stuff, but instead I'm going to be walking you through the very exciting, the very powerful tooling of CGO-less foreign function interface with WebAssembly. So I hope you can enjoy it. But you know, in retrospect, WebAssembly or WASM has been quite a buzzword in the last couple of years, right? I can imagine everyone has ever heard of the phrases like, you know, WebAssembly is the next coming technology, or WebAssembly is trying to replace everything, and WebAssembly is trying to become containers, which I don't believe. But anyway, so, you know, it's been quite a buzzword. But the real question, though, is that how it's relevant to you and how it's relevant to normal Go projects, normal Go application developers, right? Because we've already known that you can compile Go applications to WebAssembly by setting Go OS equals JavaScript and the Go architecture to Wasm, right? But it's only for JavaScript, so it seems like it's only for web. But the reality is that you can use WebAssembly for non-web projects, actually, as a Gopher. So that is a topic I'm going to be talking about, so I hope you can enjoy. So let's get started. So let me start with this simple question. So how many of you can explain what exactly foreign function interface is? Okay. Quite a few. Okay, so let me share some of the examples or definitions from Wikipedia. So it's basically about calling non-Go functions from Go, right? So maybe C functions or Rust function or Zig functions or whatever. So now we have main.go. Maybe you want to call Rust function, right? It's pretty cool. And also maybe you want to call Zig function, which is my favorite language, and actually I'm being a contributor to the compiler, so which is my another story. But anyway, so maybe you want to call these foreign functions, right? So very fancy, but sometimes you might want to do this kind of things. But why? Why do we need foreign function interface in the first place? So the one motivation behind a foreign function interface is that, you know, some of the softwares written in non-Go languages are worth reusing rather than rewriting, right? Maybe you have 1,000 lines of C, then you don't want to rewrite everything from scratch in Go, but rather reuse it, and it's going to save you a lot of hours of time, right? And also, you might wonder, is it possible to have plugin system over FFI, right? So for example, if you have HTTP server application, maybe you want to allow your users to extend your HTTP server with their own favorite languages. So that is where foreign function interface comes into play, right? So very, you know, very strong motivations behind FFI usages. So let's get back to this example. We are trying to call very simple empty functions, right? There's no parameter passing. There's no results back and forth between the boundary between Go word and foreign function word. But once you introduce complex signature, the things will get more complex, right? So the question will be like how to pass parameters between the boundary and how to accept the result between the boundary, right? So the question is like this: what's a protocol between the boundary of Go and another languages? And also, we are writing Go. That means we are heavily relying on Go runtime, so we don't want to mess them up, right? So we don't want to, avoid destroying Go runtime when doing foreign function calls. So this is why we have CGO in the first place in the official compiler toolchain. So with what CGO does is that it manages all the parameters and the results between a boundary. So instead, you can just calling foreign functions just like any other pure Go functions, and everything, the rest of it will be taken care by CGO. Cool, right? So this is what CGO does, and CGO is actually the implementation of foreign function interface. Cool. So if I can be done, so my talk has finished. Cool. But the reality is that no, right? Because we know CGO is not Go. So how many of you have ever heard of this? I think, oh, cool. So CGO is not, it's a very famous one, so you should check out this YouTube video. So anyway, let me recap on the, some of the CGO related issues. So let me review some of them. So first one is that about portability of produced binary, right? Because one of the most important benefits we can have from the official compiler toolchain is that we can easily produce the fully static binary in case of Linux, right? So let's compile this hello world example, right? Build it, and let's check the binary is fully static or dynamic one. And sure enough, it is not a dynamic executable, right? But once you insert import C statement, which is a mandatory statement when you're using CGO, then things will change. And when you check the binary, you will find that your binary is dynamically linked to the libc, in this case, Ubuntu machine. So that means your binary loses its portability. So, for example, you cannot run this CGO binary on the Scratch container where shared library doesn't exist. So that is the portability issue you would incur when using CGO. And the next one is also about portability. So it's very easy to compile or cross-compile your source codes into any platform with CGO. But once you enable CGO, you shouldn't be able to easily cross-compile. So this is example. For whatever reason, I'm trying to compile Hugo with CGO enabled on Macintosh, and I failed because all the C portion of your program and the comparison of them are beyond the scope of Go official compilers. So you have to take care of everything rather than relying on Go official compiler toolchain. So that is the reason why we are losing cross-compilation features when you're using CGO. So the next one, I think this is controversial, so I don't want to go far deeper into detail. But so basically, foreign functions do not know anything about Go runtime. So in other words, CGO will manage their own Go routine stack and doing context switching in order to avoid messing up Go runtime. So they're basically doing heavy context switching. So as a result, when you are making a lot of CGO calls, then that could be the bottleneck of your application, because making a large amount of CGO calls means that you are doing a large amount of context switching in CGO. So that is one of the major performance issue associated with CGO. So if you're curious, please check out GitHub. So, and the last one is very important and most relevant to WebAssembly. So let me talk about the security aspect of CGO. So now we have foreign functions and CGO. We are using CGO. So your foreign functions will share entire operating system and including the virtual memory space with the original Go functions. So in other words, when you have the malicious code in your foreign function, then your operating system resources and the virtual machine, virtual memories are vulnerable to the malicious attackers. So I'm not saying that pure Go application is free of malicious code. I'm not saying that, But instead, what I'm trying to say is that you are basically expanding the vulnerability surface of the operating system, because foreign functions, the comparison of foreign functions are beyond the scope of Go official compilers. You have to take care of everything, security aspects of them. So basically, you are expanding the vulnerability surface when you're using CGO for foreign functions. So what can we do? We need sandbox, right? With sandbox, we can isolate these malicious codes, possibly malicious foreign functions, from the operating system. Then we can protect your operating system in the virtual memory space used by your main Go function. So how can we do? So this is where I'm introducing WebAssembly to this talk, right? For those who don't know anything about WebAssembly, let me do some of the one-on-one. WebAssembly is basically the simple binary instruction format for stack-based virtual machine. It's a pure virtual one. And it has some of the notable features. But one is that just like any other native hardware like AMD 64, 64, it is said to be polyglot, meaning that in theory, this is kind of controversial topic, but in theory, any programming languages can be compiled to WebAssembly. So that's why we say WebAssembly is polyglot. And also, it has a lot of security-related features with WebAssembly. So let me explain two of them. One is that memory guard, and that is the way I call it. So for example, when you're running Linux binary or ELF binary on Linux or maybe Ubuntu machine, your program, possibly containing malicious code, can access every single part of the virtual memory space where you place your program global variables, including function call frame stacks or stack pointers, whatever. So in other words, your program can modify anything. And so, for example, they can hijack control flows because they can modify control frame stack, right? So on the other hand, WebAssembly, code frame stack or virtual value stacks are isolated from the original virtual memory space. So in other words, possibly containing, maybe you might end up having malicious code in Wasm binary, but that malicious code cannot modify the control flow. So they cannot hijack the control flow of the Wasm execution. That is what memory guard is about. And also, it has a very exciting and a very interesting feature with respect to system calls. That is, we have denied by default system calls mechanism in WebAssembly. So your WebAssembly program will never be able to make any system calls. And they have to be allowed explicitly by the operating system or host runtimes. So that is what denied by system calls is about. So, but this is a natural question from WebAssembly beginners, right? Because the word WebAssembly contains a web, so it is weird if we can use it for non-web use cases, right? But the reality is that it is weird, and we can use WebAssembly for non-web use cases. The reason is that if you take a look at the specification of WebAssembly, you will never be able to find any web browser or JavaScript or HTML of these kind of words. But instead, the WebAssembly specification is purely about the binary instruction format and how these binary instructions are executed on that virtual machine, and that's it. So it's nothing to do with the JavaScript or whatever. So that's why we can embed that general virtual machine in your application. In our case, we can embed that Wasm virtual machine inside your native Go applications. So that is why we would say Wasm is not only for the browsers, even though the word Wasm contains a web. It's pretty cool. Actually, there is a lot of example on non-web use cases of WebAssembly out there. I believe one of the most popular one is Envoy proxy, which I had worked on in the last couple of years. And with Envoy proxy, which is allowing us to use the mechanism called proxy wasm. And a proxy wasm is kind of like an interface to extend the proxy with WebAssembly binary. So for example, you can use the WebAssembly binary to extend or change the default proxy logic of Envoy proxy. So it's very cool and a very exciting one. And also, there's a project called Tetrate, and Tetrate is, I think, the re-implementation of some part of Kubernetes. And it's basically allowing us to run WebAssembly as a container inside your Kubernetes cluster. So it's a very exciting one. So let's get back to this example. So what we wanted to have a sandbox, right? Sandbox over possibly malicious foreign functions. So now that we have WebAssembly, we can have sandbox over these foreign functions because we can compile your foreign functions into WebAssembly. So now we have sandbox. Cool. But the last question is how to run them, because even though we have WebAssembly binaries, we have to execute them inside your Go applications, right? Because WebAssembly, as I repeated, WebAssembly is just a virtual one. You need the runtime implementation or virtual machine implementation, which runs that virtual instructions on top of the real hardware, like ARM64 or AMD64. So this is where I'm introducing my own project called wazero.io. And its tagline says that the zero dependency WebAssembly runtime for Go developers. So what is wazero? It started out as my hobby project back in, I don't remember, 2000, maybe 21. And now it's sponsored by Tetrate since last year, and now I'm fully working on it full time. So yeah. And wazero is, as I said, the runtime implementation WebAssembly. So basically, wazero allows us to run WebAssembly binary inside your Go applications without relying on CGO. And also, as the name indicates, it has zero dependency. So if you take a look at my repository, you will find that it has complete empty Go mode. So I've developed everything from scratch, only relying on the standard library. So please check out my repository. So now that we have wazero, your foreign functions are compiled to WebAssembly, which has sandbox. And that WebAssembly binary can be run by wazero inside your Go application without using CGO. So now we've achieved the talk title, right? CGO-less foreign function interface with a WebAssembly. So now we can, it's possible with wazero with WebAssembly. So now we can have FFI without CGO. Cool. So let me explain some of the advantages over CGO. Of course, no CGO is the most important one. No CGO, so meaning that you can keep cross-compilation and also static binary and anything like that. And also zero dependency, as I said, so you don't need to messing up your Go mod file. Wazero is gonna just add one line into your Go mod, so it's very something I'm proud of. And also, the third one is the most notable feature, right? Because you can just compile your foreign function into WebAssembly and once. And that WebAssembly can run on any platform because everything will be taken care by wazero. On the other hand, when you are using CGO, you have to compile your foreign function to every platform you have to support. So that is a clear difference. You can have compile once into WebAssembly and run it everywhere. And also, by nature of WebAssembly, it has sandbox environment by default, which is a very cool feature of FFI with wazero versus CGO. So let me explain some of the sandbox feature, or how memory isolation, how system call isolations works in practice with wazero. So now we have Go program, which is using wazero, and we are trying to run Zig virtual machine and Rust virtual machine inside your Go application. And each virtual machine will have some of the linear memory or virtual memory, which can be accessed by your Wasm binary. And that linear memory is implemented by simple byte slice in Go. So in other words, from WebAssembly point of view, every single memory access to the linear memory will be translated or interpreted as the access to the byte slice. So it's very simple interpretation. So as a consequence, these foreign functions will never be able to access other parts of the memory space. So this is a clear difference, because when you're using CGO, your foreign functions have access to the arbitrary range of memory space of Go program, right? So this is a very clear difference. So the next one is about system calls. So as I said, WebAssembly has something called denied by default system call, right? So in this case, these foreign functions trying to read file, write file, but they need access to system calls, right? But when you're using wazero, all the system calls will be implemented by you, or wazero users. So you have full control over how system calls works, and how to deny, when to deny, anything like that. And instead, that Go function is considered as the system calls will access the actual operating system resources instead. So the clear notable feature is that your foreign function will never be able to access the actual operating system. That is the case with CGO, right? So we have full control over how system calls works when you're using wazero or WebAssembly as the mechanism for foreign functions. So to simply put, system calls are Go functions implemented by you, and the memories are just byte slice. And just like this Gopher, everything is just a smaller part of the entire Go program, and your virtual machine or foreign functions will never get out of it. So cool. So let me explain some of the example APIs of wazero. So first of all, you have to create something called runtime, and then you will create the virtual machine from the Rust binary or Zig binary. And these two variables named as Rust or Zig, that is the virtual machines. And we can use that virtual machine to call the exported function from the virtual machines. So it's very simple, and I hope you can easily understand how it works. So this is what it looks like when you are trying to call foreign functions with wazero and WebAssembly. So let me introduce some of the example projects, example users of wazero. So one is that I think everyone knows about it. I don't know. Trivy is a very famous scanner, vulnerability scanner, and it has a mechanism called Trivy modules, which basically allows us to run WebAssembly modules to extend the default functionality. So very, very powerful features. So if you are interested, please check out their documentation, because they have a lot of extensive documentation. So yeah, please check out. And also the next one, I hope I'm pronouncing correctly, but Dapper is basically the serverless platform. And the Dapper has the HTTP middleware, which is extensible by WebAssembly, and that is implemented by wazero. So please check out. And also, I have created some of the two example projects for this talk. And one is about SQLite. And I think everyone is like this topic. So basically, I succeeded in running SQLite compiled as WebAssembly and inside your Go application without relying CGO. So what's interesting about this is that this can be the possible implementation of a CGO-less and sandbox SQL driver interface. So it's very exciting. And so I haven't implemented any interface yet. So, but if you're curious, please check out my repository. And also, my colleague and I are trying to use the C++ library called RE2. RE2 is a very fast regular expression engine. And we succeeded in running it inside Go application without relying single. And what's very exciting about this is that in some benchmark cases, it's much faster than the standard library of Go. So it's not for all the cases, but some cases it's faster than the standard library. So I've already praised some of the benchmark results on the repository. So if you're curious, please check out. It's a very exciting one. So I think I've already covered the good parts of wazero and WebAssembly, but also I have to explain disadvantages over CGO. So first one is that to some extent you have to expect performance degradation or performance penalty because, as I said, WebAssembly has sandbox by default. So in other words, it's kind of like virtualization. So you cannot get virtualization without having costs. So you have to expect to some extent. And also, even though I said you can compile once and run everywhere, but you still need to compile once. But that is a problem because WebAssembly's ecosystem is quite, I would say, premature. So you might encounter some of the issues when you are trying to compile your existing project to WebAssembly. For example, the current state of WebAssembly specification doesn't contain anything about threading or atomics. So in other words, if your foreign functions are relying on these features or semantics, then it's impossible to compile it to WebAssembly. So that is a reality. And also, even when you don't encounter these glitches, maybe you still have to refactor in a WASM-friendly way. I think it's hard to explain, but this is real. So this is an example. As I said, we succeeded in running RE2 as a WebAssembly, but this is a screenshot from my friend, my colleague, and he is trying to compile RE2 to WebAssembly, but it turns out that he has to add thousands of lines to the library. So this is a real, but you have to brace yourself. But I hope it will improve in the future. But this is the real. So I think I'm finished with the main parts of my talk. So I think it's time to answer deep dive question if you're curious. So first question, as a wazero users, I think you might wonder how it's correct. Because implementing a virtual machine, the instruction, the binary format, and that kind of things should be difficult and should be complex, right? But I'm proud to announce that wazero is 100% compliant with the existing WASM specification. So we have 1.0 and 2.0. And 1.0 is the W3C recommendation, and 2.0 is still W3C draft state. But we're compliant with both of these specifications at the same time. But how it's tested? How can I say that it's compliant with the specification? Because WebAssembly specification has something called spec tests, and which allows us to make sure that our virtual machine implementation or runtime implementation is correct. And luckily, we are passing 100% of specification tests, and that is why I'm saying that wazero is 100% compatible with specification. And not only that, I'm also doing the random binary fuzzing to find out every edge cases in our implementation. So I'm confident that the bugs in wazero are now pretty rare. So I think it's reaching some of the stable point. So yeah, that is how wazero is tested. And also, you might be curious about how it's implemented and how the execution works actually in the first place. So we have two modes. One is that interpreter mode, and the second one is ahead of time compiler mode. So let me explain each of them. So in the interpreter mode, it can run any combination of Go OS or Go Arc, right? Because it is interpreter. It has first startup time, as you expect, but it is slow because it is interpreter. And on the other hand, we also have a ahead of time compiler mode, which can run ARM64 or AMD64 combined with Linux or Debian or major operating system. And as you expect, it is compiler, so it has slow startup time, but instead it is much faster than interpreter, like 10 times or 100 times faster than interpreter. You might wonder, how it's even possible, right? Generating machine code at runtime and executing it, that shouldn't be possible in the normal Go world, right? But actually, I agree that it's not possible with normal Go world. You have to hack the Go runtime. So here are the three things, what AOT compiler works, what AOT compiler does. The first one is that we are generating the machine code, for example, ARM64. We're generating ARM64 binary from the original Wasm binary, which is semantically equivalent. And then the generated machine code is just a byte slice. So we're memory mapping it, and so that we can mark this byte slice as the executable. And then the last step, we're transferring the control to that generated machine code at runtime via Go assembly function. So here's a diagram, how each step would correspond to wazero API. When you are creating virtual machine, wazero is trying to generate machine code, which is semantically equivalent to the original Wasm binary, and then memory mapping all the Wasm functions as the executable. Then when you are calling any exported function from WebAssembly virtual machine, we're transferring the control to that heap allocated machine code. So this is how it works. So let me share some of the code snippets from the actual implementation of wazero. We've actually implemented all the, ARM64, M64 instruction formats, and then I'm using that assemblers to translate the Wasm SIMD instruction, for example, this case, translating SIMD Wasm instruction to that equivalent ARM64 instruction while keeping the semantics of WebAssembly. So this is what actually the machine code generation of compiler works. And then we are memory mapping, as I said. This is not something interesting one. We are just memory mapping that generated machine code as executable. And then last step, we're actually transferring the control of the function execution to that specified ARM64, M64 machine instruction address via Go assembler function, which allows us to do some of the jumping, right? And also, of course, I have to admit that I've faced a lot of challenges because this kind of thing shouldn't be possible in reality. So I have to, come up with a lot of things So, but luckily I managed to make it happen and make it work very well with the current state of Go runtime. I'm not sure for the future, but current state it works well. At least the current state of the Go runtime. So the two things, it's very important, and maybe you're not interested anymore, but basically you shouldn't modify Go routine stack when you're doing this kind of things. The first one is that, when you're manipulating Go routine stack from that machine code, then you're going to mess up garbage collection because they don't have any information about such a runtime generated AMD64 or ARM64 instructions. Of course, they have no way to know it. So you shouldn't modify Go routine stack. And also, you shouldn't access Go routine stack allocated variables, because we have something called Go routine stack shrink and Go routine stack grow, right? It can happen at any time. And when you are accessing the specified variable on that Go routine stack, then that address can change anytime. So it's very dangerous. So it can be, can result in invalid memory access. So we shouldn't access that Go routine stack or Go routine allocated variables, right? So this is what we ended up. So everything is allocated heap, and every WASM information, the modular information, the WASM stack, and everything is allocated on heap, and we are only accessing that heap allocated variable because heap allocated variables will never change its address. That is the caveat in the Go garbage collection. As of now, I'm not sure about the future, but as of now, it can work. So these heap allocated variables will never change the address, so it's safe to access from that runtime generated machine codes. So as you can see, we will never touch Go routine stack so that we can avoid messing up Go runtime and Go garbage collection. All right. Also, so debugging is extremely difficult when you are doing this kind of thing. So I wouldn't recommend anyone does this. So because runtime generated machine codes doesn't have any debugging information, so you will never be able to have stack traces and anything like that. You have to actually check the registers allocation, the register variables, and so on in order to debug it. So it's very tough, and I don't want to do it anymore. And also last one, so the current implementation is just a simple compiler, so optimizations are yet to be done. So if you're curious, please help us. So I think I'm already almost done. So let me wrap up. FFI is basically about calling a non-Go function from Go. And CGO is the implementation, but it has some issues. And as an alternative to CGO, you can use WebAssembly and wazero so that we can avoid CGO. So wazero is written in pure Go, and it has zero dependency. So, all right, thank you everyone. I hope you enjoyed it.